Hi, welcome to the video on electron domain geometry or EDG versus molecular geometry or MG. So as we know, VSEPR structures are useful because they help us predict shape and to predict the bond angles. Now, from the shapes, there are two types of geometries that we can determine from VSEPR. The first one is the electron domain geometry, and that describes the arrangement of bonds and lone pairs, meaning it describes the arrangement of all the electron domains. And this is determined just by the number of electron domains. So no matter how many lone pairs you have in a structure, if you have a certain number of electron domains, it will have this name electron domain geometry. On the other hand, the molecular geometry, also known as the shape of the molecule, describes the arrangement of bonds only. And for that, we ignore the lone pairs. Since we ignore the lone pairs, we need to know how many lone pairs we are ignoring. Therefore, the molecular geometry is determined by both the number of electron domains and the number of lone pairs a structure has. So far, we talked a lot about the molecular geometries. When we were trying to identify what the shapes meant, we focused on molecular geometries or shapes of molecules, meaning we ignored the lone pairs. So now it's a good opportunity to sort of take a step back and look at both electron domain geometries and molecular geometries to see how the two are related and different. In our first example, we're going to start with the molecular geometry or shape, and that's because that's the one we talked about the most in just recognizing shapes. So again, for this one, it's determined by the number of electron domains and lone pair, and we're only focusing on the bonds. So for example, if you have NH3, and I drew NH3 not in a Lewis dot structure fashion, but in a VSEPR fashion. So remember, this bond means it's coming, the darker wedge bond means it's coming out at us, the dash bond means it's going back away from us, and this is on the plane of the board. So we can trace the shape of this molecule, and we have sort of the shorter pyramid shape, and so the molecular geometry here is trigonal pyramidal, so a shorter pyramid with a trigonal triangular base. Now, this structure has 4 electron domains and one of them is a lone pair. And any structure with 4 electron domains and one lone pair is trigonal pyramidal. So you would need both of these pieces of information, number of electron domains and lone pairs, to explain why it's trigonal pyramidal. Electron domain geometry, on the other hand, we consider both the bonds and lone pairs. If we go back to our tracing of NH3, when we were finding out the molecular geometry, we ignored the lone pairs. We didn't include that in our tracing, right? We just focused on the bonds and the atoms here. So let's see what that would look like if we included the electron domains. So here we have NH3 again, and to make sure we include the lone pairs in our electron domains, I'm going to use this lone pair bubble. All right, and now I'm going to do the same thing I did before and trace the structure. So I'm tracing my structure, and we can clearly see by including the lone pairs, we have a taller structure here, a taller pyramid, and this is tetrahedral. So the number of electron domains here for anything that has 4 electron domains, as NH3 does, will have a tetrahedral electron domain geometry. So just to sort of recap, for electron domains geometry, you need to know the number of electron domains and include the lone pairs in the shape. For molecular geometry, you focus on just the bonds, and so for that you need to know the number of lone pairs you are ignoring. So you need to know both the number of electron domains and lone pairs. Let's take a look at another example. Here we have water. And starting with the molecular geometry, we can see by ignoring the lone pairs, we can clearly trace out this angular or bent shape. If we focus just on the bonds, we can clearly trace that out. And anything with 4 electron domains and 2 lone pairs will have this angular or bent shape. Now let's look again at the electron domain geometry, which is determined by all the electron domains. So we'll have to include the lone pairs, and again I'm going to use these lone pair bubbles. And I'm going to trace this shape out now using the lone pair bubbles. Okay, so once again, we see we have this sort of taller triangular pyramid, and so we have this tetrahedral structure. And it's tetrahedral because it has 4 electron domains. Just like in the previous example, it doesn't matter how many lone pairs it has, if it has 4 electron domains, it's tetrahedral. Okay, one last example here. We have CH4 now, and so again, I'm going to start with the molecular geometry or shape, and I'm just going to trace out the shape here. And this shape is tetrahedral. And that's because it has 4 electron domains and 0 lone pairs. So anything with 4 electron domains and 0 lone pairs will have a tetrahedral shape. Let's check out the electron domain geometry. Pretty sure by now you should know what it is. If it has 4 electron domains, it will have a tetrahedral shape. Okay, so what you may notice here at this point is that the EDG and MG are the same. And that's because whenever you have 0 lone pairs, the electron domain geometry and molecular geometry will be the same because you have no lone pairs to ignore. Remember, in the MG or molecular geometry, you're ignoring the lone pairs. But if you have no lone pairs to ignore, both EDG and MG are the same. Okay, I want to quickly look at the VSEPR chart here, to sort of take a step back and see what we've already just discovered. So in all the examples we looked at, they all had 4 electron domains. And if they have 4 electron domains, their electron domain geometry, which is this center column here, is tetrahedral. On the other hand, for the molecular geometry or shape, we have to know how many lone pairs it has in order to figure that out. So, for example, the case where we had 4 electron domains and 1 lone pair, it was trigonal pyramidal. In the case where we had 4 electron domains and 2 lone pairs, it was angular or bent. And when we had 4 electron domains and 0 lone pairs, it was tetrahedral. And remember, anything with 0 lone pairs, the electron domain geometry and molecular geometry will be the same. Now let's try some CFUs. So for our first CFU, you have the structure here of SO2. I want you to determine the number of electron domains and lone pair first in SO2. And then determine the electron domain geometry or molecular geometry of SO2. And I drew it in this VSEPR function structure so that you can determine it just by looking at it and not having to use the VSEPR chart. But you're welcome to use the VSEPR chart if that's helpful. All right, so pause the video now and do your work on separate scratch paper. When you press play again, the answer will be revealed. Great, so this structure has 3 electron domains, 1, 2, 3, and one of those electron domains is a lone pair. Now, let's go into the shapes. So for electron domain geometry, we are going to include the lone pair. So if I draw my lone pair bubble in and then trace out my shape, I can clearly see it's a flat triangle or trigonal planar. So the EDG is trigonal planar. Now for the molecular geometry, I'm going to ignore the lone pairs, and if I just trace out the molecule through the bonds here, I see I get this angular or bent shape. And so the molecular geometry is angular or bent. All right, let's try our final CFU. So for this one, you have a structure with, they tell you that a structure with 5 electron domains has a trigonal bipyramidal EDG or electron domain geometry. I just want to pause here. We are not going to be required to figure out the trigonal bipyramidal shapes, but just note that that is another shape. Okay, so if it has 5 electron domains, it has a trigonal bipyramidal electron domain geometry. Based on that information, which molecule has a trigonal bipyramidal molecular geometry, and explain. All right, you have these 3 molecules to choose from. Pause the video now. When you press play again, the answer will be revealed. Okay, the answer to that is molecule 2. So let's take a look at why. Molecule 2 has 5 electron domains and 0 lone pairs. So we already know that something has 5 electron domains has electron domain geometry. Because molecule 2 has 5 electron domains and 0 lone pairs, its molecular geometry will match its electron domain geometry. Let's quickly look at why the other molecules are wrong. Molecule 1 has 5 electron domains, but one of them is a lone pair, so therefore it's not going to work. Molecule 3 has 6 electron domains, so it doesn't even matter how many lone pairs it has. Because it has a different number of electron domains, we can't rely on the fact that its molecular geometry will quite match up. All right, so that's it for this video. Hope you found it helpful. Have a quality day.